Good question. When you are using the ampersand operator to get the address of something, the onus is on you at the moment to know what you are getting the address of. Is it a string? Is it a char? Is it a bool? Is it an int? I wrote this code, so I know in line 6 that I'm trying to get the address of what is an integer. In line 8, you don't have to worry about that. Good question. Notice in line 8, I didn't tell the computer, other than the %i, what kind of address I'm going to. But I did already. In line 6, I told the compiler that p, now and forever, is going to be the address of an int. That's enough information in advance so that printf, or really the language C, still knows on line 8 that p is a pointer to an int. And that way, it will print out all 4 bytes at that address, not just part of it, and not more than those 4 bytes. Good question. Yeah, next to you. Do pointers have pointers? Yes. We won't sort of do this today by having pointers to pointers. But yes, you can use star, star, and then things get in. I'm sorry. We won't do that today, and we won't do that often. In fact, Python, another language, is just a couple of weeks away. So hang in there. Almost there. Question back here? Was there? That was amazing. Good. More verbal feedback like that is helpful as we forge into the more complicated stuff. Other questions? Yeah. What's the point of printing the address? Like? Sure. What's the point of doing this? If you don't mind, let's get there in a moment. This is not the common use case, just printing out the address. Like, who really cares? At the moment, we care only for the sake of discussion. We're soon going to start using these addresses. So hang in there just a little bit for that one, too. But it will solve some problems for us before long. So let's actually just now depict what was going on inside of the computer's memory just a moment ago. So if I toggle back here, let me redraw my computer's memory, and let me plop into the memory n, which is storing in this program the number 50. Where is p in my computer's memory? Specifically, I don't know, and apparently it moves around each time I run the program. So for the sake of discussion, let's just propose that if 50 ended up at address 0x123, I don't know, p ends up over here at address, at whatever address this is here. But notice a couple of curiosities now. If p is a pointer, it's the address of something. So the value in p should be an address. And I've indeed written it as such, 0x123. And technically, there's not an x there. There's not a 0 there. There's not even a 123 there, per se. There's a pattern of bits that represents the address 0x123. But again, that's week 0. Don't care about binary day to day. So if this is p, and this I claimed was n, why is p so much bigger? Can someone conjecture here? Because it turns out whether n is an int or a char or a bool, which are different types, heck, even a long, it turns out that p is always going to take up 8 squares on the board. But why might that be? What might explain that? Yeah, thoughts? OK, fair. Maybe it's allocating 8 bytes because it doesn't know the type. Turns out that's OK, because an address is an address. It's really up to the programmer to use it as a string or a char or a bool. Other thoughts?
Maybe like the first chord for the actual numbers and the last chord, like some null thing where you say that, oh, well, where that pointer ends.
OK, possibly. It could be that pointers have some complexity, like a \n or something curious like that, like we talked about for strings. Turns out that's not the case. It turns out that pointers nowadays typically are, but not always, are 8 bytes, aka 64 bits, because you and I, our Macs, our Ps, heck, even our phones, have a lot more memory than they did years ago. Back in the day, a pointer might have only been 32 bits, or even only 8 bits, way back in the day. But consider 32 bits, because that was the norm for some time. How high can you count roughly if you've got 32 bits? What's the number we keep rattling off? 32 bits is roughly 2 to the 32. So it's 4 billion. And I keep saying it's 2 billion if you do negative. But in the world of memory, there's a reason I keep saying 2 billion bytes, 2 gigabytes, because for a very long time, that was the maximum amount of memory a computer could have. Why? Because the pointers that the computers were using were only, for instance, 32 bits. And with 32 bits, depending on whether you allow for negatives or not, you can count as high as 2 billion roughly, or maybe 4 billion. But you know what? Your Mac, your PC, your phone could not have had 5 gigabytes of memory or 5 billion bytes of memory. You certainly couldn't have had what computers nowadays come with, which might be 8 gigabytes of memory, 16 gigabytes of memory. Why? Because with 4 bytes or 32 bits, you literally physically can't count that high, which means if I drew a picture of all of the memory, we would run out of numbers to describe them, which means like most of my memory would just be unusable. So pointers nowadays are 64 bits or 8 bytes. That's really big. I can't even pronounce how big that number is, but it's plenty for the next many years. And so we've drawn it that way on the board here. Now let's just kind of abstract this away. Let's get rid of all the other bytes that are storing something or nothing else. And let's now start to abstract away this complexity, because the reality is, to your question earlier, what is this useful for, or do we actually care about these addresses? Generally, no. We're doing this so that you see there's no magic. We're just moving things around and poking around in memory. But what a person would typically do when talking about pointers would literally be to just point at something. Like, I really don't care what address n is at. So it suffices when drawing pictures on a whiteboard, having a discussion with another programmer, you just kind of draw an arrow from the pointer to the value in question, because neither you nor I probably care about the specifics of 0x whatever. So there's your pointer. It's literally an arrow. And we can kind of see this. So it turns out that these pointers, these addresses, are not that dissimilar to what we've done for hundreds of years in the form of a postal system. For instance, here's a post office. Here is a mailbox. And suppose that this is a mailbox labeled P. It's a pointer. And suppose there's another mailbox like way over there, which is just another byte of my computer's memory. What are we really talking about? Well, you store in a computer's memory values like the number 50 or the word like hi inside of your computer's memory at some location. But today, we can also use those same memory locations to store the address of things. For instance, if I open this up here and I see, OK, the value inside of this mailbox is not a number like 50. It's actually an address, 0x123. That's kind of like a pointer, sort of a breadcrumb leading from one location in memory to another. And in fact, would someone who's seated roughly over there, do you mind getting the mail over there? Any volunteers over in this section? Just need you to get to the mailbox before I do. Who's being volunteered? Oh, yes, please. Whoever is gesturing most wildly. Come on down. Sure. What's your name? Say again? Anfu? OK, come on up to the edge of the stage there. And just to be clear, if this is P, that is apparently n. But to make clear what we're talking about when we're storing 0x whatever values, like 0x123, that's essentially equivalent to my, maybe pulling out something like this and just abstractly pointing to your mailbox there, or if you prefer, pointing to the mailbox. OK, all right. Oh, thank you. All right. This is akin to me pointing at your mailbox. And if you want to go ahead and open your mailbox and reveal to the crowd what's inside your mailbox, labeled N. All right. Thank you. We have a CS50 stress ball for your trouble. Thank you for coming up. So that's just to put a visual on what it is we're talking about, because it can get very abstract, very cryptic quickly when we're talking about addresses and memory and drawing it like these little squares. But if you think about just walking into a post office or an apartment complex that's got a lot of mailboxes, those mailboxes essentially are a big chunk of memory. And each of those mailboxes has an address. This is apartment 1, 2, 3, apartment 2 billion. And inside of those mailboxes can go anything that can be represented as information. It could be a number like n or 50, or if you prefer, it could be a number that represents the address of another mailbox. And this is akin, really, if you've ever had an apartment or you and your parents have moved, to having a forwarding address. It's like having the post office in the US put some kind of piece of paper in your old mailbox saying, actually forward it to that other mailbox. That really is all a pointer is doing. At the end of the day, it's just a number, but it's a number being used in a different way. And it's the syntax that we've introduced, not just int, but int star, that tells the computer how to treat that number in this slightly different way. All right, any questions then on this. Yeah, in back. If I did int c and set it, can you say the code again? Once more? Equal to n. So let me actually type it out. If I give myself another line of code, tell me one last time what to type. Int is equal to n like this. So this is OK. And I can't draw it quite quickly enough on the board here. But this would be like creating another 4 bytes somewhere in memory, maybe down here, that stores an identical copy of 50, because the assignment operator from right to left copies one value to another. So that would just add one more rectangle of size 4 to this particular picture, if I'm answering your question as intended. OK, so that is sort of week 1 style use of assignment operators before pointers. I could, though, start copying pointers. But again, we'll come back to some of that complexity. Any other questions here?
That was a great question. Does the pointer point, does the same pointer point to the new replica as well?
Ah, good question. Short answer, no. And to repeat for the camera, if I create a second variable like this, int c equals n, and I claim, without actually drawing it on the board, that this gives me another rectangle, the value of which is also 50, p does not get touched. And this is what's important and really characteristic of C. Nothing happens automatically for you. Like, p is not going to be updated unless you update p in some way. So creating a third variable called c, even if you're copying its value from right to left, that has no effect on anything else in the program. A good question. So what have we seen that's perhaps now a little more explainable? Well, recall that we talked quite a bit last week about strings. And just to recap, in layperson's terms, like, what is a string as you now understand it? Say, let me take a specific hand here. What's a string? How about over here? OK, sure. Both of you are right. An array of characters. An array of characters. And I claimed or revealed last week that string is not technically a feature built into C. Like, it's not an official data type. But every programmer in most any language refers to sequences of characters, words, letters, paragraphs, as strings. So the vernacular exists, but the data type doesn't typically exist per se in C. So what we're about to do, if you will, for dramatic effect, is take off some training wheels today. The CS50 library, implemented in the form of the header file, cs50.h, we claim has had a bunch of things in it. Prototypes for getString, prototypes for getInt, and all of those other functions. But it turns out it also is what defines the word string in such a way that you all can use it these past several weeks. So let's take a look at an example of a string in use. Here, for instance, is a tiny bit of code that uses the word string, creating a variable called s, and then storing quote unquote hi exclamation point. Let's consider what this looks like now in the computer's memory. I don't care about all the other bytes. Let's just focus on these. And this, per last week, is how hi might be stored. hi exclamation point, and then one more, as someone already observed, that sentinel value, that null character, which just means 8 0 bits to demarcate the end of that string. Just in case there's something to the right of it, the computer can now distinguish one string from another. So last week, we introduced this new syntax. Well, if strings are just arrays of characters, you can then very cleverly use that square bracket notation and go to location 0 or 1 or 2, which are kind of sort of like addresses, but they're relative to the string, right? This could be at 0x123 or 0x456. But with this bracket notation, 0 is always the beginning of the string, 1 is the next, 2 is the next, and so forth. So that was our array syntax for indexing into an array. But technically speaking, we can go a little deeper today. Technically speaking, if hi is starting at the address 0x123, then it stands to reason that I is at 0x124, exclamation points at 0x125, and the null is at 0x126. Now, I don't care about 123 per se, but even though this is hexadecimal, this is correct math. Even in hex, if you just add 1 when you start at 0x123, the next number is 4, 5, 6 at the end. I don't have to worry about A's, B's, and C's because I'm not counting that high in this example. So if that's the case, and my computer is actually laying out the word hi in memory like that, well, what exactly is s? Right? What exactly is s if at the end of the day, hi exclamation point null are stored at these addresses. Like, where is S? Like, now that I've kind of taken off those training wheels and showed you where HI exclamation point null actually are, what happened to S? Well, S, as always, is actually a variable, right? Even in the code I proposed a moment ago, S is apparently a data type that, yes, doesn't come with C, but CS50's library makes it exist. S is a variable of type string. So where is S in this picture? Well, it turns out that S might be up here. Again, I'm just drawing it anywhere for the sake of this discussion. But S is a variable per that line of code. What S is storing, apparently, I claim, is OX123. I actually don't really care about these addresses, so let's abstract that away. S is apparently, as of now, today, 1 week later, just a pointer to a character, specifically the first character in S. And this is kind of the last piece of the puzzle. Last week, we had this clever way of demarcating the end of a string. Well, it turns out that strings are represented in the computer's memory as a variable that is a pointer, inside of which is the address of the first character in the string. So if S is points at the first character, and you can trust that \0 is at the end of the string, that's literally all you need to figure out where a string begins and ends. So what do I mean by this? Well, let's be a little more concrete. In terms of this picture, if I've started with this line of code here, it turns out all this time since week 1 that the word string has just semi-secretly been an alias for char star. I know, so char star. So why does this make sense? It's a little weird still, but if in our previous example, we were able to store the address of an integer by declaring a variable called p as int star p. Well, if as of now, strings are just the address of the first character in a string, then probably a string is just a char star, because that means S is the address of a character, the very first character in the string. Now, the string might have 3 letters like it did, or 4, or even 100 if it's a long paragraph. But that's fine, because you can trust that there's going to be that null character at the very end. So this is a general purpose way of representing strings using this new mechanism in C. So in fact, let me go ahead here and introduce maybe a couple of manipulations of this. Let me go back to my code here. And let's get rid of this integer stuff. And let's instead now do, for instance, this. Let me add in the CS50 library. So we'll include cs50.h for now. I'm going to go ahead and inside of main give myself a string s equals hi exclamation point. I don't type the \0. C does that for me automatically by using my double quotes like this. Now let me just go ahead and print it. So this, again, is sort of week 1 style stuff where I'm just printing a string. No pointers yet. So let me do make address, enter, /address, and hopefully I see hi. So nothing new there. But let's start to peel back some of these layers here. Let me first of all get rid of the CS50 library for a moment. And let me change string to char star. And it's a little bit weird, but yes, the convention is to say char, a space, then the star, and then immediately thereafter the name of the variable. Strictly speaking, though, you might see textbooks or websites that do it like this or like this. But the canonical way is typically to do it like that. So now no more CS50 library, no more training wheels, if you will. I'm just treating strings for what they really are. Let me go ahead and do make address, enter. So far, so good, /address. And that too still works. So %s is a thing. That comes with printf, because the word string is programmer terminology. But strictly speaking, C doesn't have a string data type. It's always been char star. So what this means now is I can start to kind of have some fun with these basic ideas, even though this is not purposeful other than for the sake of discussion. But if S is this, let me go back and give myself the CS50 library. Let's put those training wheels back on for just a moment so that I can do one manipulation at a time. Here's my string s, as before. Well, let me go ahead and declare a char called C. And let me store the first character in the string there, which is s bracket 0. And that should give me h. And then just for kicks, let me go ahead and do char star, whoops. Let me go ahead and do char star p equals ampersand c, and see what this actually prints for me. Let me go ahead and print out what p is here. So we're just playing around. So make address. So far, so good. /address. All right. So what have I just done? I've just created a char c and stored in it the letter H, which is the same thing as s bracket I. Then I'm saying, what's the address of C? And that's apparently 0x7ff whatever. So that's the address. But I technically didn't have to do that. Let me go ahead and do two things now. Instead of just printing P, let me go ahead and print out maybe S itself. Let me go ahead and do make address, enter. So far, so good. /address. And damn it, what did I do? Oh, shoot. I didn't want to do that. Oh, I really made a mess of this. What did I want to do here? That was supposed to be impressive, but it was the opposite. So let me turn it around. So if I intended to do this, why are lines 9 and 10 printing different values? Didn't really intend to go here, but let me try to save this. Why are we seeing different addresses? Namely, this address, 402004 for S, and then 0x7ff for P. Any thoughts? Yeah, over here. Correct. So if I really wanted to weasel my way out of this, this is a great answer to the previous question, which was about what if I introduce another variable C that's a copy of the value, and not in this case an int, but an actual char. Here, I've made C be a copy of the character that's at the beginning of S, but that's indeed a copy. So if I were to draw it on the screen, that would give me a different rectangle in which this copy of H would actually be stored. So I didn't intend to do this, but what you're seeing is, yes, the address of S, and apparently that's at a pretty low address by default here. Then you're seeing the address of C, but even though each of them is H, I claim one is at a different address in memory. And this has always been happening. Anytime you created one variable or another, it was ending up here or here or here or somewhere else in memory. Now, for the first time, all we're doing is actually just poking around the computer's memory to see what is actually there. So let me actually back this up a little bit and do what I intended to do here, which was something like this. So if string s equals quote unquote high, let's go ahead and give myself a pointer called p to the first character in s. All right. So now let me go ahead and print out the value of this pointer, %p, printing out p. So we're just going to do one thing at a time. So make address, enter, /address. There at the moment is the address of the first character in s. What I meant to do now was this. If I want to print out two things this time, let me print out not only what p is, but also what s itself originally is. Because if I claim that everyone from last week should be comfortable with s bracket 0 just representing the first character in s, by definition of strings being arrays of characters, then s, as of today, is itself the address of a character, the first one in s. So if I now do make address and do /address, this time I see the same exact things. Thank you. This is really like the lamest sort of thing to be applauding over. But what we're demonstrating here is that s is by definition the address of the first character in C. So if we borrow some of our mental model from last week, well, if s bracket 0 is the first character in C, doing the ampersand on that expression should be the same as s. Now, this isn't to say that we would kind of jump through these hoops all the time with this much syntax, but this is just to do proof by example that s is, in fact, as I claimed a moment ago, just the address of a character, not even multiple characters. It's the address of a single character. But the key thing is it's the address of the first character in the string. And per last week, we trust that C is going to look for that null character at the very end just to make sure it knows where the string actually ends. All right, a question came up over here.